In this video, we're going to look at some example calculations using isotopes. So I'm just going to do a quick review of what you've learned about isotopes, hopefully from the book and the PowerPoint, and then we'll work on some problems. So the definition of an isotope, it's atoms of the same element that have different mass numbers. So since they have different mass numbers, it's because they differ in the number of neutrons. So let's look at what neutrons are. So what I have off to the left here is a very simplified depiction of an atom. So this center blue circle is representing the nucleus, and inside the nucleus we have protons and neutrons. So that's what these two symbols here mean. The P with a plus sign for protons and the N with a 0 for neutrons. So the protons and neutrons, those two subatomic particles, are located in the nucleus of an atom. You then have rings around the atom, and on these rings are where the electrons are going to be located. So electrons are often represented with this E to the negative sign. That is because electrons are negatively charged. So let's look at the properties of these three subatomic particles. So protons are centered in the nucleus, and they have a +1 charge, is why they're represented with a P to the plus. Their mass is 1. The neutrons are neutral, so they don't have a charge, so their charge is 0, and their mass is also 1. So you'll notice that most of the mass of an atom is located in the nucleus of an atom because that's where the protons and the neutrons are. Now the electrons on these surrounding rings, they have a -1 charge. And notice we write their mass as 0. Their mass isn't actually 0. It's just so small that we consider it negligible, and so we count their mass as being 0. And what we have here in an atom is, since the protons and neutrons are located in the nucleus of an atom, the overall charge of the nucleus is going to be positive. So we know this because protons have a +1 charge and neutrons are neutral. So our overall charge in the nucleus, since it contains those two subatomic particles, would be a positive. So since the nucleus is a positively charged center consisting of most of the mass of the atom, the electrons are then orbiting that positive nucleus. So the reason the electrons are orbiting it is because electrons have a negative charge, and we just said that the nucleus is an overall positive charge. We know that opposites attract. So those negatively charged electrons are attracted to that positive center nucleus, causing them to orbit it. Now, using what we know, the properties of these three subatomic particles, we can figure out not only how to calculate the mass number, but also how to calculate the charge. So charge we're going to look at more closely in a different video. But if we wanted to figure out the charge of a particular atom, we would take the protons and add the neutrons together, because those are the only two subatomic particles that have a charge. So neutrons aren't needed. We don't need to know how many neutrons are in an atom when we're figuring out charge, since they don't contribute to the charge. For mass number, and that's what we're going to be focusing on in this video, you would take the protons, which have a mass of 1, and add it to the neutrons, which also have a mass of 1. Notice we are not taking into account the electrons, because since their mass is so small, we don't count it towards the total mass number. So the reason we're focusing on mass number in this video is because isotopes by definition are atoms of the same element with different mass numbers. So we need to know how to calculate the mass number of different isotopes. So when we're representing isotopes, they're represented in two different ways. One way is with a nuclide symbol, and I have an example of a nuclide symbol here. So we represent a nuclide symbol by first putting the element symbol here. So instead of X, we would put the element symbol, and you can get the element symbol from the periodic table. So carbon, for instance, if you looked up carbon on the periodic table, you would see its element symbol is C. Then in this upper left-hand corner is where the mass number goes. So this is going to be a whole number, and that is the total protons and neutrons in that particular isotope added together. Now in the bottom left-hand corner, this is where the atomic number is going to go. So for the atomic number, this is equal to the number of protons. The atomic number you can also find on the periodic table, written just above the element symbol. The other way that we represent isotopes is by writing the element name. So we would literally spell it out. So for carbon, we would write C-A-R-B-O-N, and then a dash, and then following would be the mass number. All right, so let's look at some representations of isotopes and what type of calculations we might need to do. So I'm going to start by giving two isotopes. So my first one I'm going to look at is bromine 79, and then bromine 81. So these are two isotopes because they are both atoms of the same element, because they're both representing bromine, and their mass numbers, this number in the upper left-hand corner, are different. And the reason those mass numbers are different is because they have a different number of neutrons. So notice this bottom number, the atomic number, is the same in both isotopes. The reason the atomic number is the same is because the atomic number represents the number of protons. And the number of protons defines the element itself. What that means is if I change the number of protons, I'm changing the identity of the element. So if I change this from 35 to 36, for instance, I'm no longer talking about bromine. I'm talking about a completely different element because the number of protons defines the element. That is something that does not change given our particular element. So all atoms of bromine will have 35 protons every time. Their mass number might change because they might have different number of neutrons, but their number of protons will not change. All right, so what would we do given these nuclide symbols? So one question that might be asked of you is to calculate the number of protons, neutrons, and electrons. So given that nuclide symbol, you should be able to figure out all three subatomic particles. Well, the protons, that's the easy part. That's this bottom number here, right? And the bottom left is the number of protons. So that's going to be 35. Number of neutrons. So how do we figure that out? Well, we just looked at the definition of a mass number. And mass number was the protons and neutrons. So I know the mass number, that's this number up here, right? That's my mass number. I also know my number of protons because that's right here. So I know this guy and I know this guy, so I just need to solve for him. So to figure out the number of neutrons, you would take the mass number and subtract the number of protons from it. So the nice thing about the nuclide symbols is they're set up already for you to calculate that. Imagine putting a line here and then a subtraction sign. So I'm taking mass number minus the number of protons. So 79 minus 35 gives me, what is that, 44? So I have 44 neutrons. Now for the electrons, how do we figure that out? Well, for that we look at charge. Okay, so we said for charge, you would take the protons plus the electrons, because protons have a +1 charge, electrons have a -1 charge. Well, what is the charge of this atom overall? It's actually neutral. How do I know that? Because if there was a charge, it would appear in this upper right-hand corner. Okay, so if it was a -1, a +1, a -2, +2, that would appear here. The absence of there being a charge tells me that this bromine isotope is neutral, meaning it has an overall charge of 0. So if the charge is 0 and the number of protons is 35, how many electrons do you think we have? We're also going to have 35. Since electrons are negatively charged, 35 plus a negative 35 equals 0. So, in neutral atoms, protons are going to equal the electrons. Let's look at the second isotope and do the same thing. So I'm going to do protons, neutrons, electrons. Protons, 35, because we're still talking about bromine. It's neutral, there's no charge, so my electrons must be 35 as well. So neutrons is the only thing I need to calculate. And remember, to do that, we're taking the mass number and subtracting the number of protons. When it's set up like this, we can simply put a line here and subtract the two. And in this case, we're going to get 46 for the number of neutrons. So these are isotopes of each other because they're two atoms of the same element. They're both bromine, and their mass numbers differ because their number of neutrons differ. Bromine 81 has 2 more neutrons than bromine 79. All right, let's do another example. This time, let's use our other representation of an isotope. So we're going to do iron 57 and chlorine 37. And I'll do chlorine 37 over here. So for these, we're going to do the same thing. We're going to figure out the number of protons, neutrons, and electrons. But we're also going to take this representation and write it as a nuclide symbol. So let's start by writing it as a nuclide symbol. So iron. So how do I represent iron-57 as a nuclide symbol? Well, I would find iron on the periodic table and figure out what its corresponding symbol is. When I find iron on the periodic table, the corresponding symbol that I get is Fe. So I would write Fe. What's going to go in this upper left-hand corner is going to be the mass number, and that's what this is here, dash mass number, so 57. Now, I don't have to, but I can put a number down here. And the number that goes down here is going to be the atomic number, or the number of protons. So let me get out my periodic table to find that. So when I find iron, Fe, let's see, where is that guy? Right here, so it's number 26. So that number 26, that's the atomic number. That's the number of protons. So I'm going to write 26 down here. So it didn't particularly tell us, or specifically tell us, how many protons were in it. But since we know the identity of the element, we can figure out the number of protons. Because these are tied together. The protons and the identity are tied together. If I change the number of protons, I change the identity. So 26 is my number of protons. It is neutral. You can only represent neutral isotopes in this format because there's no place to put a charge. So it has to be neutral if you represent it this way. So that means there's also going to be 26 electrons because protons and electrons have to equal each other. So they cancel out to make a 0 charge. Now for the neutrons, you subtract the 2. So what do we get? 31? 31 neutrons for that isotope. So there's our subatomic particle count, and here is our nuclide symbol representation of that isotope. Let's do the same thing over here. So chlorine-37. So to find the symbol, I would look up chlorine on the periodic table, It's number 17. It's a halogen. So its symbol is Cl. So I'm writing the symbol in place of this X. I'm writing Cl. In the upper left-hand corner, I'm going to put the mass number, which is the number that comes after this dash. And then down here, I would put the number of protons. And I just said that chlorine is number 17 on the periodic table. That number 17 is how many protons it has. That's the atomic number. So it has 17 protons. It's neutral, so it also has 17 electrons. For the number of neutrons, I'm going to subtract these two, and I get 20. Good. So that is how we are going to be doing calculations with isotopes using nuclide symbols as well as this other format.